Okay, so today I'm going to talk about, I'm going to review neural networks and deep leaf networks and kind of show how they are similar and how deep leaf networks came about and their motivation, stuff like that. If you have any questions, just stop me. Okay, so I'm going to go over some terminology just to make sure we're all on the right page. This is what graphically a neural network pretty much looks like. Each of these circles here represents either neurons, nodes, or units. We'll just use neurons. Those words are used interchangeably within the literature. The connections between neurons represent the synaptic connections in the brain, and we're just going to call them weights. And then each one of these is called a layer. And then we'll consider that a structure or configuration is a number of layers, is defined by a number of layers of number of neurons in each layer and the presence or absence of a connection between different neurons. We'll say that a given neuron is active if the value is 1 and inactive if the value is 0. So, for example, this is one activation assignment to the network. This is another one. So that when I say activation assignment, I mean a setting of all the nodes to a particular value. Okay, so does everyone understand how this is a neuron? Okay, so I don't need to go through all of that. All right, so we have two types of neurons. We have deterministic neurons. We compute the output of this weighted input, and then we sigmoid, and then if it's greater than 0.5, we say it's active, and if it's less than 0.5, we say that it's inactive. There's also probabilistic neurons. So this output here is so the sigmoid function, the range is between 0 and 1. So we can treat that as a probability that the node or the neuron is active. And so when we're looking at probabilistic neurons, what we do is we compute the output and then we make the neuron active with probability, whatever the output is. That process is called sampling. So this is done by choosing a random number between 0 and 1. And then if that number is less than the output, then you set the neuron to active. If it's greater than the neuron, it's inactive. I'll also be putting all of this stuff on online, including the notes and the video. So, don't worry about too much about writing everything down. Okay, so here's an example of sampling. Let's say that this is our network, and we've already set the nodes here to 1 and 0, and these are our weights. And our bias for this unit is -0.1. So we'll compute the output, and the output we computed here is 0.57. And so we can take one sample, first step. Can you guys see this down here? So the first step is to randomly generate a number. Let's say that we randomly generated 82 or 0.82. Then we take, then we know that the output which was 0.57, is less than 0.82, so the neuron is inactive. So we set this to 0. We can take another sample. Let's say a randomly generated number was 0.35. That's less than the output, so this would be a 1. Then we can do another one. Let's say the random number was 0.14. 0.14 is less than 0.57, so again, the neuron is active. So what we've just done is created 3 different samples of this node, given that these nodes are set. So that's what I mean when I say sampling. Okay, so is anyone confused on how we go from images to vectors? Does everyone understand how the images are, the visible nodes in networks are the image? Does everyone understand that? Okay. So, does anyone not understand it? Okay. So in the network we normally have some visible nodes, and so these are set by the data, and then we have some hidden nodes. So what are these hidden nodes? Someone have an answer. Kind of like not like nothing too specific, just kind of like an intuitive answer. So hidden nodes are nodes that we don't see. So there's visible. Oh, I said I was going to use neurons the whole time, but I use nodes here. I hope it's not confusing. So in this network, there's the visible nodes and there's hidden nodes. So the visible ones are the ones that we see. They're visible, and we see them through the data. And then the hidden nodes are ones that aren't in the data, but we're hoping to maybe use them to kind of do something that we want. So, for example, we might want to have a hidden node detect whether or not an image is a horizontal line or a vertical line. So maybe we want a network where the structure of it consists of however many pixels are in here are in the visible layer, and then there's a single node, and it's connected to all of the pixels in the visible layer. And we want this node to be, let me see what I did. All right, so we want this node to be close to 1 if there's a horizontal line, and then we want this node, and we want the same network, so like the weights here correspond to the same weights here. We want this hidden neuron to be a 0 if it's a vertical line. So in this way, a hidden neuron is basically detecting whether or not it's a vertical versus horizontal line. Does that make sense? Yes?
If it's noise, is it just something in between?
Yeah, so so this is all right now we're just talking about this is the whole data set. And we just want to be able to detect between these two, and we assume that it's always going to be those two. Does that make sense how does that make sense how I made that network there? I don't know if that. Okay, so these things are images, and if it's white, that means that it's a value of 1, and if it's black, then it's a value of 0 for each pixel. All right, so all right, this is basically what I just said, because I didn't need to draw it, I already had it. Okay, so what would a good set of weights be for such a network? So let's say that we'll represent this as, so each one of these is a pixel, and we'll say that the weight, the value in here is the weight that corresponds to the weight of, that the hidden unit is connected to this pixel, and so forth. So what would be kind of a good way to set these weights so that the neuron is close to 1 when it's a horizontal line, but close to 0 when it's a vertical line? They don't need to be exact values or anything, kind of just a general intuition. Okay, so we want, so each one of this is a 1. These are 1s here too, and then 0 is where the black is. So what pixels are on when it's a horizontal line but not a vertical line? I'm sorry?
One's on the left.
Right, so if this is an image normally like around here, there'll be a lot of on pixels, but in the vertical case, a lot of the pixels will be on here. Oh shoot. That's not what Okay, I actually want to go and do something about that before it dries. I didn't use a projector because I was scared I'd wipe right on that. It's a good idea to do that. Okay. All right, so if you remember, our sigmoid function looks like this, and so the larger the weighted input is, then the closer it'll be to 1, and the more negative the input is, the closer the output will be to 0. So we want to set the weight so that when there's a lot of pixels right here, the weighted sum is very high. But then when there's a lot of pixels here, the weighted sum is very low, or very negative rather. So what we would have is something that looks like, we would have something that has really high values, let's say, just make them like 100, or I'll just say 1. All the values, all the weights here are 1. And then all the weights here would be negative 1. And then everywhere else 0, basically. So does that make sense how this neuron would then encode these two concepts? Yep.
Would you want to flip the 1 and negative 1 if you're detecting horizontal?
Yes. Isn't that good? Sorry about that. Okay, yeah. So yeah, that's basically it. Okay, so that's an example of how a hidden unit can detect a concept from the input. And the input. Okay, so that's basically this. Okay, so now how do we do that? It's really, obviously we could hand code that for that example, but we're not going to be able to do that with kind of more complex concepts. So the way we find such a set of weights is by we compute the error for every set of weights, and then we try and find the set of weights which has the lowest error. So again, this is the sigmoid output function, and for a given set of weights, you can compute the error, and the error is the output given the weights minus the target output. So let's say that the output for all of the horizontal ones were 1, and all of the vertical ones were 0, then t would be 1 for all of the horizontal lines and 0 for all of the vertical lines. And then we take the squared, so basically the squared error. Does this make sense? Any questions?
What
Yes.
is the examples in this case? Or do you want us-
I'm sorry?
What is examples? Is it the pixels?
Oh, okay, so we will be computing the error of a weight, of a set of weights given a set of data. So the set of data, or the examples, are those 8 images that I showed in our running example. Okay, so we can view kind of all of the errors across all the different weight possibilities as a surface, and our goal is to find the lowest point on that surface. So let's say we have an example where there's in two dimensions. So let's say that we have, these are our data points, and we want the label is 0 if the left pixel is darker than the right pixel. So the pixel here is lighter than that, so it's a 1. Pixel here is lighter than that, so it's a 1. Pixel here is lighter than that, so it's a 1. So let's say that this is x1, this is x2. All of these values are x1 and all of these values are x2. Then a good set of weights would be something like I think that's right. Just double check. So this was. Yeah, that's right. So basically, so the lighter it is, the higher the value is, and so this will subtract this value from this value. And so if this value minus this value is positive, then this value is lighter. I got that backwards. Sorry about that. So, alright, so we want to subtract this value from this value so that it's 0 when this value is higher than this value. Does that make sense? So let's say that this is like the intensity here is I and the intensity here is J. So J is going to be greater than I, and in that case the label is 0, so we want it to be the case that this value here is negative, and that will be the case because x2 is greater than x1, j is greater than I. Does that make sense? Okay, so given this example, this is what the error surface would look like for this example. So if you were to make the complete opposite thing, like how I originally did it, you would have high error because you would basically be predicting 1s for 0s and 0s for 1s. But then if you have something like this, it corresponds to the lowest error point, and then there's different values in between. Any questions? Okay, so how do we do this? So what we do is use gradient descent, and an analogy of gradient descent would be trying to find the lowest point on a hill when you only are able to see maybe 3 feet in front of you and around you. So the way you would do that is if you were just plopped randomly in Frick Park here, let's just say right here, and you could only see around you maybe something like this big, and you wanted to get to the lowest point, a good idea would be to take a step in the direction of the steepest descent, so that you just continually are taking steps downward. And so maybe you start here, and then you take a step here, and then take a step here, and then eventually you'll continue to get lower and lower and lower until you get to a lower point. But unfortunately, that's not going to guarantee us to get us to the minimum, because there are normally in error surface many local minima and maxima, so that it could be the case that you ended up going right here, maybe you started right here, and you got down to here, but then it turns out there's a lower energy minimum here than you would have gotten to if you started here. So we have this problem of actually finding the lowest point is intractable. It's actually, I think, it would be hard. Okay, so that's an analogy how we do this in math. So the hill is the error surface. The direction of the steepest descent is the derivative of the error at a certain point with respect to the weights. So if we start off with a weight set right here, we can take the derivative of this error surface at that point. And what that gives us is the direction of the steepest descent. That is the derivative. So when you compute the derivative, the vector you get is that direction. And then taking a step corresponds to updating the weights in the direction of the computed derivative. Any questions? Okay. All right, so you guys can look at this math later. It basically just goes through how the derivative is computed. All right, so this method, so this is called gradient descent. You can use stochastic gradient descent. So in regular gradient descent, you have to go through all of the data examples before you take a single step. In stochastic gradient descent, what you do is you do it after a few examples or one example. And this allows you to update the weights quicker or more often, because you don't have to go through all of the data. You can just go through some of the data. Another name for stochastic gradient descent is called batch gradient descent, in which you use a batch of examples, normally 10 to 100 or so, to compute the derivative of the error, and then you take a step. This is something you have to know about for the homework. In the homework, you use batch gradient descent so when you're computing the learning rule for the restricted Boltzmann machine. Okay, so this method can be generalized to a multi-layer network with backpropagation. So you can compute the error with respect to any of these weights and then update them accordingly. So these things are pretty powerful. I think it was in the 90s, Jean Pomerleau was then a PhD student here, and he was working on using neural networks to create an autonomous land vehicle, and it worked pretty well. This is it driving through Flagstaff. If you're interested, there are some videos about it. Okay, so there's some shortcomings in neural networks. First, you need labeled data, because you can't really do any learning without labeled data. And there's much more unlabeled data in the world. It also it learns by minimizing the error on training data, which means that you only gather information between data and labels. You're not really gathering any information about the data itself. Learning doesn't scale well with multiple hidden layers. And you can get into poor local optima. So we're now going to talk about restricted Boltzmann machines and deep belief networks, which will have a different learning objective, which will allow it to learn from unlabeled data, and it will use a greedy training algorithm, which allows it to scale to multiple layers very easily. And we still have this problem where when we're trying to learn a deep belief network or a restricted Boltzmann machine, that we're going to have this problem where we can get into local optima. But the thing is that we can use what we learned from the restricted Boltzmann machine or the deep belief network to then initialize a neural network to help a neural network not have to not have such a problem with this problem. Any questions? Okay, so before we were talking about trying to detect this concept, and we came up with a pretty good weight set that would do a pretty good job. But it turns out that if you run a neural network on this data, you might get something that's a lot simpler. So you might just have a weight set in which it chooses a single pixel. Let's say that the pixel here, 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 and here are the same. They're just the same pixel. They might not be, but just say they're the same. And then the pixel here, 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 and here are the same. Meaning that this is the ij pixel, and same with this. Now, in all of these cases, these pixels are on, but they're off here. And then vice versa for the pixels here. So basically, the neural network could have learned a weight set in which it only, all of the weights are 0 except the value here, which would be very negative, let's say like negative 1,000,000. And then the value here is positive 1,000,000. And then everything else is 0. And yeah, it would still do a pretty good job. It might be able to classify them all correctly, but it's kind of not as interesting because it's not really getting an idea of what a horizontal or a vertical line is. And the weight set that we created had a better idea of what a vertical and horizontal line actually is. Does that make sense? Does it make sense how a neural network could possibly learn a weight set in which all the weights are 0 except for these two, and still get the lowest error, or a low, the minimum error? Okay, so this kind of shows what I was talking about, where there's the information between data and labels can be very, very low. There can be not that much information in that channel because it could just be communicated with just 2 weights. Okay, so now we're going to talk about restricted Boltzmann. We're going to start talking about restricted Boltzmann machine. I'm going to motivate it with a few examples. Basically, the restricted Boltzmann machine tries to represent the world instead of just trying to classify or detect certain things. So instead of having a hidden node detect certain things, the hidden nodes try to basically explain the data or capture something about the data. So I want to do a few things to motivate this. The first thing is I'm going to pass around my lab code, and I just want you guys to take a look at this and notice that when you look at this, weird things happen. Your eyes might not, you can take it, and you might want to like make sure it's wide and maybe move it up closer to you and further away from you, and just do you notice that like things aren't very stable?
Yeah.
So it's not really showing you what's actually there. Alright, so I don't know how well this is going to work on the video camera, but we'll give it a shot. Okay, so now I'll try and explain why that might be. Alright, so look at these two images. This is image 1, image 2. We'll look at it for 10 seconds. 1, 2. Try and think about like the differences between these two images. Alright, was this either the first or second image? The second? Okay. Why do you say that?
I think there's more white space on the left side.
What do you mean? Well, I mean, you might be right. Actually, I don't even know the answer.
Doesn't
Wait, these are.
looks like it's
Left.
there's like a black blob on top.
Yeah, so if you look really close and you look at something really in particular, you'll be able to find it. But if you just look at the image as a whole, it might be tough. Hey. I don't know. Let's give you some context of what we're doing. So, take a look at this. Do things move a bit? Okay.
Yeah.
So right now we're talking about why that might be.
Okay.
And this is motivating a restricted Boltzmann machine / deep leaf network. All right. So these are two images. Now, what's interesting about these two images is statistically they're very much different than each other. Yet we still can't really. Given these two images, we can't really figure out was that image or the other image very easily. So let's do another example. All right, so I'll give you 10 seconds. All right, was it the left or the right? It's a trick question. They were actually both the same. They were both the same, we can even tell. So what's interesting about this is, okay, so then that's image. All right, but now we have two images here. All right, was it the left or was it the right? All right, it's a lot easier, right? Because you've seen cats before, and you've seen landscapes like that. But in your general day-to-day life, you don't walk about and have this pop up in your visual field. And so there's kind of this idea that the brain learns to represent the world efficiently. So it won't learn to represent things that it doesn't see, that it doesn't like come across. So here's some evidence for that idea. So in 1970, I think Colin Blakemore and people in his lab did this experiment where they had a cat once, since he was born, he or she was born, they had the cat either be in complete darkness or the only time it was ever in light, it was in this cylinder in which there were only vertical lines. Then they had another cat where it only lived in a cylinder in which there was horizontal lines. So basically one cat only ever saw horizontal lines and one cat only ever saw vertical lines. And then what they did was after a while of the cats being in this or that, like months or so, I think they waited to the point, the kind of like the critical period for vision in cats. And then what they did was they probed the neurons in early visual cortex to see what they liked. And the one that existed only in a vertical environment, all of its neurons were tuned to vertical stimulus. So what these images predict are each line represents a neuron, and the orientation of the line is that neuron's preferred orientation. So basically, all of the neurons were encoding horizontal lines in the cat that existed in the horizontal cylinder, and then the opposite for the cat that existed in the vertical. Now, it wasn't just the case, and I put a video down here, which shows some behavioral experiments in which they would take so it wasn't just the case that like the neurons were responding, but like maybe they were still seeing vertical. So maybe it's still the case that even though the neurons are selective to horizontal lines, it's still possible that the cat can see vertical lines somehow. And so what they did was they had behavioral tests in which they took, let's say, the cat that only saw vertical lines and would have a bar and kind of put it in front of it and move it around, and the cat wouldn't respond at all. But if they made it vertical and then moved it around, the cat would move its head around to follow it. And there was a bunch of other behavioral experiments to kind of show that that its behavior was predicted by its environment. So this is some evidence of how, like, the brain will, depending upon its environment, or depending upon things that it has seen in the past, it'll change or reorient itself so that it optimally represents the environment. Does that make sense?
Was did the cat was the cat ever able to develop normal vision?
Yeah, so I think they did this, like they were in here for like a few months, and then they did the experiments right afterwards, and then I think a few months afterwards they couldn't tell the cats from the regular cats that didn't undergo this and were just running about the world however they pleased. Yes?
Did the cats see themselves before or no? Or did they
I don't think so. I think so. They had this collar on so that it couldn't look at itself. They couldn't look at its legs, and I don't think there were any mirrors around. So this was like glass and the stuff that went down. Another experiment was done later by people at MIT in which they used goggles. So like they really were only ever seeing certain lines. Because in this they could see like not vertical lines because they could like kind of move their head, so you could get different images. Okay. So now we want to engineer this world representative. So we want to kind of like keep the same idea of a neural network because that's our kind of representation, or mathematical representation of neurons. But we want to have the hidden nodes kind of be able to represent the world. And the way that we do that is we try and change the weights in such a way that the hidden nodes could reconstruct the visible layer. And so basically, if the hidden nodes can reconstruct the visible layer, then that means that the hidden layer itself somehow represented the visible layer or the image. Does that make sense? I can explain that more if not. Okay. So the way we do this is, before we were basically trying to learn the probability of the label given the data. So we're basically trying to find this mapping between the data and the label. Now what we'll try to do is maximize the probability that if this network generated the data, then it would generate, we want to change the weights in such a way that when the network generates a visible layer, the visible layer is something like the data. Okay, so I'm going to go off the slides now. Okay, so we're talking about restricted voltage machines, and I'll have to explain, I have to talk about kind of how we represent these things before I continue on this discussion. Okay, so in a restricted Boltzmann machine, we have basically this is a bipartite graph in which every node in the visible layer is connected to every node in the hidden layer. And these are undirected connection, which is unlike a neural network, or a regular feed-forward neural network. So with a restricted Boltzmann machine, we can compute the energy of a given activation assignment. So I'll use V and H to represent a vector of hidden activations. So H would equal, in this case, like let's say this is 1, 0, 1, and H would be 1, 0, 1. And then now let's think for this whole layer. Okay, so this is the energy of a given activation assignment, where Wij corresponds to the weight or synaptic connection between the visible unit I and the hidden unit J. C corresponds to the visible biases, and B corresponds to the hidden biases. Is anyone confused on what biases are? Basically, the biases represent how often the neuron will be on in general, given independent of its input. It's kind of like the spontaneous firing rate. Okay, so so then we have the probability of a given activation set. Assignment rather, and it is so the probability of a given activation assignment is the is e to the negative energy of the assignment over the sum of the e to the energy of all other assignments summed together. So basically, you would compute the energy for all the possible assignments, and so in this case, there are so each one of these can take a value of 1 or 0, so there's 2 to the 3 possible ways to configure the hidden nodes, and then there's 2 to the 5 possible ways to set the visible nodes, and then you could, for each one of these, you could have one of a different one down here. So we multiply these to count the number of possible ways. And so basically, I mean, in a network like this, it's not very large. It's, I guess, 8 times 32, which is a few hundred or so. But when you're using a really big network, you have something like 2 to the 1,000, and that might be bigger than the number of atoms in the universe. So basically, it's going to be impossible to compute this. But the thing is when we're worried about the probability, we don't have to when we're worried about the relative probability between 2 configurations, we don't have to worry about this because this is always going to be the same. This is a constant. So really, this is proportional to e to the negative e to the h. Okay, so energies, probabilities, what's going on here? How does this make sense? How does an energy convert to a probability? So let's say that we want the connection between 2 nodes to be really strong. And so the weight would be really high. Oh, I'll be putting these notes online too, just so you know. Let's say we want or rather, let's say the weight between this node and this node is really high. That means that we want it to be the case that there's a higher probability for an assignment in which these 2 are the same. Does that make sense? Because the weights are representing the connection between the 2 nodes. So let's just look at one single connection and isolate a single connection, and let's say that it's very large. Let's say it's like 1,000. Then when let's say that these are both 1. That means that this will contribute negative 1,000 to the energy, which will then contribute basically a positive 1,000, because we're using a negative sign here, a positive 1,000 to the probability. Does that make sense? So this kind of shows how if the weights between 2 nodes are high and they're on, then you're going to have a higher probability than if they're off. Because if one of these was 0, then it would contribute nothing, and then it would contribute nothing here as well. So it would be lower. Yes?
Why is the energy, why are all the terms negative and then you do another negative sign?
Because all this came out of physics, and I think physics has some reason to do that.
Okay.
Maybe there's a better reason, but I don't know. I when I saw this thing the first time, I thought the same thing. Why are you confusing me? I don't know. So,
What's the superscript again?
Superscript where?
On the bottom of the probability.
This right here?
Yeah.
Oh, okay, so yeah, I didn't mention that. So that is, we're just saying that this is summing over all the possible activation sets. Yeah, so that's what I was counting up here. Okay, so does it make sense how weights correspond to probability? Okay, so we can compute the probability of a visible node given the hidden layer. So here we're the subscript here means that we're looking at a specific node, not the whole layer. And what this is just our sigmoid activation that we've been using the whole time. And then we can also compute the probability of the hidden node given the visible layer. So basically, this is a little different than the feed-forward networks because we only really ever compute the activation of the hidden layer given the visible layer. Now in this model, because it's an undirected graph, or an undirected model, we can compute the probability of the visible layer given the hidden layer. Okay, so we talked about before, what we wanted to do was maximize the probability that this model will generate the data. And so what that does is gives us a learning objective. So you can compute the probability of a given visible unit by summing over all the possible configurations of hidden units. It's just like kind of basic probability. So what I'm saying here is you can get this probability of a given visible layer by computing this for every single possible hidden configuration. Now that may be intractable to compute, but that's okay because we're just worried about maximizing this value given the parameters. So what this is we're taking the probability over the whole data set that the model where this probability is defined by the parameters WBC, because through that over there. So basically what this is doing is it's maximizing the probability that the model will generate the data that we saw. So what we can actually do is, what we're actually going to do is make this a log and then a sum, because that'd be the same thing. And what this equals is the expected value on the data of So does everybody get this when you erase this? Is that okay? Okay, so again, we're trying to maximize with respect to some weight. So we can do this for every single weight and for every possible weight and bias configuration. There's an associated log probability of the data. And so we can use gradient descent again to basically start at a given weight set and then use gradient descent to find or rather in this case it's gradient ascent, or descent if you take the negative. But in any case, it's going to end up being pretty much the same idea. So anyways, the derivative of this right here, so the derivative of the log probability of the data with respect to a certain weight is going to equal the expected value in which when the visible layer is clamped to the data of the product of V, I, and Hj minus the expected value on the model of the same product. Okay, so this is very easy to compute. What this is so this means the ith pixel in the dth training example. I don't know if dth is a word. Times the probability that the hidden node is on, given the visible layer, the whole layer of that training example. So we can compute this really easily. This is just our sigmoid function that I just erased. And then what this corresponds to is to get this expected value, what you would have to do is use alternate Gibbs sampling to continue to alternate the sample. And when I say alternate sample, basically if we had a set of nodes here, let's say it's 0, 1, 0, 1, 1, 0, or whatever that is, and then we compute the probability of each of these hidden nodes and then sample from it. And then what we do is, given this layer, we then compute a sample down here. Maybe it's this. So that's one step of alternate Gibbs sampling. You would then, to do another step, you do the same thing again. You sample here and then sample down here. Does everyone understand what I mean by sampling? So if you do this an infinite number of times, it'll eventually like kind of settle into what the model thinks should be happening here, and you can, given the samples, compute the expected value of the product of these units. But that's intractable because you just can't sit around forever for this thing to settle. And so it's been found that you can use something called contrastive divergence, which allows you to do it much more efficiently by just sampling one single time. Or you can use contrastive divergence K, in which you alternately sample K different times. So in that case, what you would do is now I'm going to start representing things with rectangles. So this is exactly what I just had here, and the weights are here. But I'm just talking about a whole layer at a time. Does that make sense? Okay, so first we have a visible example from the data. And then what we do is we get a hidden activation of the given the data. Then what we can do is, so basically we've done this to sample, and now we can sample another visible layer. We'll call this V1, so it's the first sample. And then we can do this again to get another hidden sample. Well, actually, I guess V0 here, V0 would make any more sense. All right, and then what this rule says is that you So instead of using the model here, in which if we were actually to compute this, then we would have to do it like an infinite number of times. We're doing the expected value after one sample of alternate good, or one iteration of alternate good sampling. So this is the efficient learning rule. Okay, and so what we do is, let's say this is unit I, sorry, I guess I'll do this. This is unit I, this is unit J, and initially this is a 0. And then this is a 1, and then this comes down here, and this is a 1, and this is a, let's say, a 0. Then the weight change would be 0 times 1 minus 1 times 0, and just in this example. And what you do is compute this over a batch of examples. So you actually sum this over like maybe B examples, if there's B examples in the batch. Okay, so let's talk about why this kind of makes sense. So I'll just rewrite the learning rule here. I'm going to use the physics notation with brackets. I think that's what Dr. Lee used. So this would be okay, so you can think of this as kind of what the model thinks the visible layer was, because this is its guess given the activation of the hidden layer. And so what we want to be the case is we want it to be the case that this will actually be very close to this. So we want to kind of push the reconstruction to be what we think it should be. So let's say that we think that initially, or let's say we have 1 here and 1 here. And so we want this thing to reconstruct a 1 here and a 1 here, because we want it to do the same thing. We don't want it to change. Because if it changed, that means that it isn't going to be reconstructing the same image. So let's say that both of these units are on, and so this value here is 1. Now, if it's the case that this value here is 1 and this value here is 1, then this value will be 1. And it makes sense, we won't change the weight because that's what we wanted. Now, if this ended up being 0 here or 0 here, then this would be 0. And then what we would get is we'd get a positive change. And so that makes sense because we wanted this connection to be very strong because they're both active at the same time. But it wasn't strong enough, obviously, because it didn't reconstruct this as a 1. And so this will end up being, so it being positive kind of makes sense in kind of what we wanted to do. Does that make sense? Now let's say that actually it was a 0 in the other case, and then, so these units aren't really strongly connected to each other, but then over here they were strongly connected to each other, then this would be 0 and then this would be 1. And so this would be a negative value, so it would make the weight less. And that makes sense because we want we don't want that weight to have a strong connection because we wanted to reconstruct something like this. But it ended up reconstructing something where they're both on. And so we want to remove some weight from that connection. And then in the case that they aren't on together here and they aren't on together here, then we'll have no change in the weight. So basically you can view this as you give the model some data and you ask it to reconstruct it and then given its reconstruction, you basically change the weights so that if you gave that same piece of data again, then you'll have, it'll reconstruct the image better. Okay. Does anyone have any questions about any of the things I just said? Yes?
Do you reconstruct like once after each, like D, each different activation set, checking Ds? So like, or do you calculate all of them and then fix all of them?
So you make a sample for each training example. So let's say that we're doing batch gradient descent and that there's 100 examples in each batch. This is the case in the homework. So you would take the first example in the batch of 100 examples and you would create this sample and then reconstruct here and then get another sample. And so you would have basically 4 vectors that represent these things. And so you would do that for all of the 100 examples in the batch. Then using those 100 examples, you calculate the expected value of these products, of these 2 products here. So, does that make sense? Did I clear it up? Yeah, so. Is there anything more to say? So yeah, if you think about this, like we're trying to reconstruct it, but we can't really do it very well because our weight set isn't kind of tuned towards these type of images. And so kind of the instability of the image that we actually see consciously is kind of skewed a bit. I mean, I can't really say that the reason that happens is because of this, but that's kind of, if you think that the brain is doing something like that, then that could like kind of explain how you're not really seeing a stable image here. Because, okay, oh yeah, so anyways, I guess I should talk about how, so now, I think I want to go back to the slides. Okay, so now hopefully this will make more sense. So if we were, let's say we learned a network in which we only showed it tubes. We only ever showed the data that it was given was only tubes. And so basically if we give it this tube, then when it reconstructs the tube, it does a pretty good job because it understands the world in terms of tubes. Now, if you were to give it a 3, then it'll try to produce something that looks like a 2 instead of the 3 because before it learned how to basically generate twos, or how to really pretty much only ever see twos. So does it make sense how when we change the learning rule to be maximizing the probability of the data, that this would happen? Because the data was only twos, and so when it generates something, it should only ever generate something that looks like a two. And so when we're talking, so this is kind of like the same idea with the cat. So the cat only ever saw horizontal, vertical lines. This deep belief network only ever saw twos, and so it's basically going to always try and see the world as twos. Okay, so okay, so that is a restricted Boltzmann machine. Now we can talk about deep belief networks. Let me see exactly. Okay, so you can. Okay, so a deep belief network is basically a stack of restricted Boltzmann machines. So what you do is you first learn a restricted Boltzmann machine in which the visible layer is the data. And then once that restricted Boltzmann machine is learned to the point where you think it's good enough, you then set that as the first kind of layer in the neural network, the deep belief network. Let me just make a white slide. Okay, so let's say we have one RBM that we've just learned. So here we have W1. So we've learned this weight set, which defines the restricted Boltzmann machine along with the biases that we've learned. And then what we can do is, given the data, we can basically sample the hidden layer for every piece of data. So if we have, say we take data piece, or the first data, and then we get a hidden activation. Then we take the second piece of data and get a second sample of the hidden layer. And so we do this for all the G examples, and then we have a and then we'll have basically a sample for every single data example. Now what we do is we treat this as data, and we learn another restricted Boltzmann machine with a different set of weights. And then to stack them, we basically just make a machine in which we have 3 layers, and the weights here correspond to the weights learned here, and then the weights here correspond to the weights learned here. And then you can continue to do this for however many times you'd like. Any questions? Okay, so before I mentioned how we could kind of ameliorate the problem of neural networks in which they kind of have to start at that random configuration, and then they kind of will end up getting stuck in for local optimum. So let's say we have this circle here represents. No, actually, let me explain something else first. Okay, so let's talk about how data and labels are generated. So let's say there's stuff. And then the stuff generates data, and I'll give examples. And then there's also labels. So for example, stuff is you and me, maybe, and data is images of our faces. And then labels are, let's say, whether or not, or labels could just be like, it's a face. And then maybe there's other stuff out there, like some other concept, and it can generate images, or there can be images generated from the stuff, and then there's labels on those, so like buildings or something. So in a neural network, regular neural network, the neural network, the first one we learned, the feed-forward network, we're learning this connection here. So basically, we're trying to figure out what's the mapping from data to labels. And in a deep belief network, what we're doing is we're trying to basically come up with some model of the stuff. So we're basically trying to learn what the stuff is, and the stuff is in the deep belief network is the stuff that's in hidden layers. So now, what makes a face is because it's a face, and not because there's an image of a face. And so it makes more sense that the labels are being generated by the stuff themselves and not the data. And so it makes more sense that data, or labels are coming from the stuff and not the data. So label that it is a face is coming from the fact that it is a face, not from the fact that it's a picture of a face. And so you can take advantage of this by first learning a deep belief network. So let's say we have deep belief network here. And we figure that somehow in the hidden layers, this stuff is being represented. Like maybe, for example, this is kind of an ideal example. If this is an image of faces, then maybe like hidden nodes will like maybe pick out certain lines, and the first layer and the second layer they'll kind of like bring together lines to make face features like eyes, nose, and mouths, and maybe and so on and so forth. Higher up there might be like an actual face detector or something. So it makes more sense that we would be able to classify whether or not an image is a face or a building, given that we have the activations up here. And so to take advantage of this, what we can do is, well, one thing we can do is we can just take these hidden activations and make them, have them be input to any discriminative classifier. So you can use like an SVM, registered regression, or anything like that. Or what you can do, if you still want to keep it in the vein of neural networks, you can add a label layer up here. So in the case of like digits, so if you're trying to learn the digits 0 through 1, maybe you'll have a layer that has 10 nodes, and one would be on, so this would be on, everything else would be off, if the example is a 0. And so now you have labels, And so you could start a neural network, instead of starting it in a random configuration, you're starting it in a place where the hidden nodes will activate what we think is the stuff. And then it will fine tune itself to get better at doing classification. And so this allows neural networks to kind of be a lot more efficient or powerful, because if you think about it, like, let's say this is the space of images, and if we have n pixels and n is 1,000, then we have 2 to the 1,000 possible images, one being like that random images that I showed you that we can really distinguish between. So let's say this is the whole space of images. Within this space, there's the space of natural images, images that actually happen in the world. And so if the thing is that if you just randomly start with a weight set, you might be somewhere like here or there or there, and you're just not in a good spot to really characterize these images. But by learning a deep belief network first, you're kind of learning what makes like a natural image, and then if you extend it into a neural network, then it will start at some place like within here. If that makes sense. Okay. Now we can make do something called we can make something called an auto encoder. So let's say that we have, I think this was the MNIST data set, which was what we used in the homework. So the initial layer was 28 by 28, and the next layer there was 1,000 neurons. They learned basically this deep belief network right here. And then what they did, and then what you do to make this autoencoder is you take the weights that are right here and put them right here, and the weights that are right here, and so forth. And so if you were to feed the data all the way up to here, right after you did that, then it would be basically the same thing as feeding up to here and then propagating it back down. Does that make sense? Because you're using the same signaling functions with the same weights. Okay, so, but by unfolding this, you can now kind of make it a neural network, because you know what the label should be, because you're trying to reconstruct the initial data. So you can use the backpropagation algorithm to fine tune these weights so that you reconstruct the data up here. And what's interesting about this is that means that when the data is right here, when it's in this layer of 30 nodes, then, and okay, so if it's the case that it can reconstruct it well, that means that this subspace of 30 nodes is representing the activation kind of characterizes the image fully, because if you have one image here and it reconstructs it, and then another image which is different and it reconstructs it well, that means that when it was here it had to be different. So this layer is somehow able to distinguish between different images. And so you can use something like this as a dimensionality reduction technique. So that's another thing you can do with deep belief networks. So there's some. So I think we did this in class. So you could compress documents, so there's this data set that consists of a whole bunch of documents on different topics from an internet forum about a decade ago or so. It's called Newsgroup 20, and what you do is you basically vectorize all the documents by word counts. Does everyone understand how that's done? I don't know if we talked about that in class. Basically, every element in the vector corresponds to a word, and the value of the element is the number of times that that word appeared in a document, a given document. So anyways, basically, you're able to represent a document in this vector, a backwards vector. And so they did this this autoencoder in which the middle layer was only 2 neurons. And they were able to still reconstruct it very well with just 2 neurons. And so if you were to use PCA on this data and try and do dimensionality reduction, you get something that looks like this, in which each color corresponds to a category of documents. So like one category would be like sports, another one would be business, another one would be dating or something or another. And this is what happens when you project it on the space of those 2 neurons of an autoencoder. And so it just somehow learns to basically distinguish between these different documents. What's interesting, I mean, this is an unsupervised technique. The learning algorithm itself did not know that all this was European community stuff and this was all energy market and stuff. It's just that the neural network was trying to always reconstruct the data, and to do that it had to be able to distinguish between these different types of documents, and also take advantage of the fact that the documents within the same category were very similar to each other. Yeah, so that's another example. So I guess that's pretty much it. Do you guys have any questions about what I just talked about at homework? Or? Okay. Cool.